I'm from Gould Instruments. Today we're at the TAFE St Leonard's North Sydney campus, who've kindly let us do some filming here to demonstrate how to test some various types of backflow prevention devices. I myself am not a plumber or a backflow testing person, so therefore we're doing it under the supervision of the Backflow Prevention Association of Australia and TAFE, of course. And we're adhering to the latest standard, which is AS 2845.3 2020. We're going to be using and demonstrating our digital instruments, which we proudly design and build in Australia. Right, the next thing we're going to do is demonstrate how to test a DCDA, which is a double check detector assembly backflow prevention device. This is a large one that would be used in the fire industry, and what it involves is a main unit, which is a backflow prevention device, and then we have a bypass or a secondary backflow prevention device. In normal flow conditions, the bypass would be feeding water to the property. Then in a fire situation, flow would happen obviously at a high flow rate through the main system. So the first thing we need to do is to make sure that the downstream isolation valve on the main backflow prevention device is closed. The inlet is still open at this stage. So we're going to do the main device. The bypass device inlet and outlet valves must be isolated so that we can test this main valve correctly. So the first thing we're going to do is just flush out any impurities from the 3 test points on the main device. That's test tap 3, test tap 2, and test tap 1. So that's nice clean water, flushed out, all good. We're going to connect the high pressure hose of the backflow kit to test point number 3 on the valve. At the moment, valve A on the test kit is open and valve B and C are closed. So we're going to hook that up to test point number 3. And now we're going to open test tap number 3. Get rid of that loose connection there. We're just going to flush out impurities through opening B and C, close B and C. Close the upstream isolation valve. So we're going to close that completely to test the integrity of both isolation valves, inlet and outlet. So we've just closed the upstream isolation valve. The downstream was already closed. At this point, we need to drop the pressure so that we can observe if it rises or falls. We can do this by opening valve B on the digital test kit to visibly drop the pressure in the system, and then close valve B again and observe the pressure to see if it is rising or falling. On a mechanical gauge, you need to do this as well, but you obviously have to drop it below 100 kPa because they don't register over 100 kPa. And then observe the pressure and carry on. I've got 114.8 kPa there. It's holding, so it means the valves are okay. If in the event that you had rising or falling pressure, you would turn off test tap 3, open valve B just to get rid of the pressure out of the line, remove the hose. Now, if you open test tap number 3, and you have a continuous discharge of water, that means that the downstream isolation valve is faulty. It must be replaced and the test reperformed, replaced or repaired. If there was a continuous flow out of test tap number 1, that would mean that the upstream isolation valve is faulty and leaking, so it needs to be replaced as well. You must always take out any line strainers and clean them or replace them at this stage. So that completes the testing of integrity of the 2 isolation valves on the main device. So now we'll move on to the next part. Okay, so we've proven the integrity of the two isolation valves, upstream, downstream, on the main device. The bypass is still isolated because that's not part of this test. The next thing we're going to do is we're going to open up the upstream isolation valve so that we restore some pressure to our valve for the next stage of testing. So now we're going to check the first check valve on the assembly, and we're going to hook up the high pressure hose to test tap 1, and we're going to hook up the blue hose, which is the low pressure hose, to test tap number 2. And on our gauge we have valve A and B closed at the moment, and valve C, which is the drain hose, is open. So the next step is we open test tap 1 and 2, and we're going to drain out any air that might be in the system and prime the system, because we want it full of water, not air, because air is compressible. So we're going to open A and just flush a bit of water through there. Then we're going to close A, we're going to open B. Get rid of, you can hear that air and that coming out. Close B, and we are going to observe the pressure. I tested the first check valve on this backflow prevention device, and we're observing the pressure. We have 67 kPa and it's holding, so it just has to be above 7 kPa to be a pass, so it's an easy pass. So what I'm going to do is record that pressure, because we need to do some calculations later on. So that's the end of the first check valve. So we're going to now do the second check valve. So the first thing to do is to turn off test taps 1 and 2. We're going to move the hoses. The low pressure hose is going to go to test point number 3. This is to test the second check valve downstream, and the high pressure hose is going to go to test point number 2. And same as usual, we're going to get the air and debris out of the system. We're going to open test taps 2 and 3, and we are going to open A, flush out any air and debris, close A, open B, and then close B, and then we're going to observe what the pressure reading is, and it has to be greater than 7 kPa, and we have a solid 30 kPa. So we're also going to record that pressure, and it will become apparent why we need these later on. So that's fine. Second check valve is fine. So we're going to close off the test tap 2 and 3. Just open A and B just to get rid of any residual pressure. Now we're going to remove the test hoses from there. So we've tested the main device, the main check valve. Now what we're going to do is we're going to test the bypass valve, which is the smaller one. So we've got to open up the upstream isolating valve to get pressure onto the valve. The downstream stays closed. And the first thing we need to do, of course, is to get any air and impurities out of the test points. So we're going to open test tap 1, test tap 2, and test tap 3. Right, so now we've got clear water coming out of those. So the first thing we have to do is check the integrity of the upstream and downstream isolating valves to make sure that they are seating and sealing correctly. So we're going to connect the high pressure hose to test tap number 3. On our test kit, we have valve A open and B and C are closed at this stage. So we've got that high pressure hose on test point number 3. we're going to open up test tap 3. We're going to bleed any impurities out of B and C and air, because we need to prime the system so that there is no air in the system, because obviously air is compressible. So we just want that gauge, hoses and the system only with air in them. So what we're looking for now is to close the upstream isolation valve, because we're trying to prove that these two valves are holding and not leaking. So we're just going to wait for the pressure to stabilise on the gauge. We always need to drop the pressure at this stage, even on the digital gauges. They've got a range of 1000 kPa, but we still need to drop the pressure so that we can observe if the pressure is rising or falling to determine if the isolation valves are leaking or not. In an analog gauge, you need to drop it below 100 kPa to do the same thing. The pressure is still dropping a little bit on our gauge, slowing down. We've got 123 kPa, so that means that both of these isolation valves are holding and they're not leaking. So that's good. So we're going to close test tap 3. Now, in the event that the pressure was rising or falling, that means that one of these isolation valves is leaking. To determine which one that might be, take the hose off. You can open test tap 3. Now, if we have a continuous flow of water, which we don't, the downstream isolation valve, if it is leaking, it must be replaced or repaired. It's mandatory. Now, if the downstream isolation valve is sound and not leaking, but you're still getting a pressure increase, you can open test tap number 1. If you have a continuous flow out of test tap number 1, that means that the inlet isolation valve is leaking and should be repaired or replaced. So that's the part of the test that proves the integrity of the isolation valves. At this stage, it's very important to clean the Y strainers on the bypass device to make sure that they are clean and not obstructed by any debris. Right, continuing on with our test, we're going to test the bypass valve now. So for a start, open up the upstream isolation valve to restore pressure and water to the valve. On the test kit at the moment, we've got valve A and B closed and the drain valve C is open. So the high pressure hose, which is the red hose, is going to go to test point number 1 on the bypass valve. And the low pressure hose, which is blue, goes to test point number 2. So we're going to put those on there. Going to slowly open test point 1 and 2 on the valve. Now we're going to bleed through any air and impurities as per usual with opening valve A, close valve A, open valve B, close valve B, and we're going to observe the pressure on the gauge. Need a pressure of greater than 7 kPa differential, and it's slowing down. Okay, we've got 12.8 kPa. So call it 13 kPa. Has to be at least 7. So that first check valve is fine. So what we're going to do now is we're going to close off test tap 1 and 2. And just open A, B, just get rid of any residual pressure. And now we're going to move the hoses to test the second check valve in this bypass device. So the low pressure blue hose is going to go to test point number 3. And the high pressure hose is going to go to test point number 2. Okay. So at the test kit at the moment, we've got A and B off and C is open. So we're going to open test tap 2 and 3 on the bypass valve. We're going to flush any air and impurities out as per usual. Open A, close A, open B, close B, and we're going to observe the pressure. Need a pressure of greater than 7 kPa. And all of these differential pressures we've been recording as we've been doing the test, and we'll explain why shortly. So we've got 8 kPa. So we needed a minimum of 7 kPa differential across the second check valve, so that's fine. So that completes that part of the test. Now I'm just going to close off test taps 2 and 3, remove our hoses. We have completed testing both the main check valve assembly and the bypass valve. So what we've done is we've recorded the differential pressures across the first and second check in the main device. 67 and 30 kPa gives us 97 kPa. And then in the bypass device we had 13 kPa on the first check, 8 kPa. That gives us 21. So it's 97 kPa combined differential pressure on the main, 21 kPa combined differential pressure on the bypass device. So clearly the main device is of a much higher pressure differential than the bypass device. Now the Australian standard AS2845.3 2020 states that the bypass device must be equal or lower in its combined differential pressure than the main device. If that's not the case, then you need to carry out repairs or replacement of the main device, and the whole test procedure must be repeated. Now you also need to check with your local jurisdiction, because rules and regulations can vary throughout different areas within Australia, unfortunately. So that concludes our testing. So now we're just going to restore the water supply to the building by opening the downstream isolation valve on the bypass, and we're also going to open the isolation valve on the downstream side of the main backflow prevention device, and that restores water. It's critical to be done, particularly in fire supply applications, of course. Right, so our water service is now restored.